morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and I think we need more cowbell, don't you? We are going to be studying intersecting planes. No need to fear them. No need to fear the Reaper, as outlined by the great Blue Oyster Cult. So let's get started, shall we? We'll turn that down, check back in with them as soon as we can. So, two planes in space. If I had two planes, they can interact in one of three ways. They can intersect in a line, they can be parallel or not intersect, or they can be coincident and be the same plane. So here we would have an infinite number of solutions for the between the equations of these two planes. Here we would have none because they never intersect, and here we would have another infinite number of solutions because they're the same plane. But if you have three planes, they could interact in 8 different ways. Okay, so they could be all coincident here. We could have two coincident, like these two green ones, and then this third one where they intersect. Okay, let's just think about the solutions here. So this would be infinite. Please write infinite solutions. Yes, infinite solutions along a line. Okay, we could have two coincident and one parallel. So while we have two planes that intersect, the third one is not in the party, so this would be no solutions. Okay. Here, two parallel, this parallel to this, and one intersecting. And while it seems like they all have intersection, they never ever have the same intersection, and nothing in common, all three of them anyway, so there would be no solutions. Three parallel, clearly no solutions. Oh, looky here. This is the only way we can have a unique solution where the three planes intersect in one point. Okay. Here, they all meet in a common line, so that would be an infinite number of solutions. And then this is kind of cool, where you have three planes, they intersect, but none of the planes share any points in common. So this would be another no solution. So if you have three planes, you have 1, 2, 3, 4 ways for them to have no solutions, and 4 ways for them to have a solution. Only one way to have a unique solution, so therefore 3 ways to have an infinite number of solutions. And I also want to show you all these different ways with equations. For example, with these 3 equations, this is an example of the unique solution. And I just want to kind of rotate this around, this neat little graph, and you can see the website and try it out yourself. And you can see right there where there is the unique solution. The next 3 are going to be the infinite solutions, and this is where, let me reset the axis, X, Y, and Z, I think you can see. You can see where they intersect in a line right there. That's kind of cool. You can really see the line. You have to imagine it going on and on forever, and I'll try and get another decent view. That's kind of cool there, and maybe back this way, but I think you can see how they intersect in one line, infinite number of solutions. Next one. What we have here is we have planes 2 and 3 here are the same plane. They're coincident. And that happens when every coefficient and the constant are multiples of one another. In other words, if I took 2 times equation 2, I would get equation 3. That's the same plane, boys and girls. So then I have a third plane, and they intersect clearly in a line, this line right here. So there's an infinite number of solutions. And of course, the other way we can have an infinite number of solutions if all of the planes are coincident. Okay, so there you go. This is kind of cool. I'm going to turn on all the grids so you can kind of see a 3D version of it. Maybe a better 3D version. This is a 3D version. So there's certainly an infinite number of solutions there. If we go here, no solutions. All 3 planes are parallel. I don't know why I like to reset the axis. I just do. But if we turn them, you can, oh, if I can get it just right. Oh yeah, there you go. You can see that there's space in between all 3 planes, so they do not intersect. Here we have 2 parallel planes and one intersecting both of them, but yet none of them ever share any point. So there's a good view of it. You can see through the two, and then you can see where these two intersect. No solutions there, because not all of them share a point. Here we have two planes that are coincident, planes 1 and 2, and then a third that's parallel to those two. And you can see how they don't intersect there. Okay, see there, nice space in between there. And then my flavor fave, is the triangle one, right? Where there's three planes and they intersect, but they never intersect in one place, and they form this triangular prism, this infinite triangular prism as they go on and on forever. I just think that is the bomb. Here's a kind of a weird look, right? And so we can twist it, and then if I get it just right, oh, we can see the space through there. So cool. Let's see if it helps with these axes in there. I think it just gets more confusing. Wait. There we go. There's another view from the other side. Okay. So we need to be able to solve these cowboys, and so let's get back to it. And we're going to do that using row operations, which I think you're familiar with. It's just solving a system of equations in 3 dimensions. You're used to ax plus by equals c, and then a1, b1, c1, and then a2x plus b2y is equal to c2, or where we would do substitution or elimination or graphing or whatever. But this is 3 by 3, and we use the same sort of idea, but we're gonna use an augmented matrix form, and all that is I list the coefficients and the constants, and then I just use a line here to separate the coefficients from the constants. Then we don't have to be bothered rewriting the variables all the time. And then we can multiply, add, subtract, just like we could do here with the elimination method. And everything's fine because we're multiplying an entire equation by the same constant. So it doesn't change the solutions to that particular equation. And the goal is to get it in echelon form. An echelon form is where you want to have a 0 here, a 0 here, and a 0 here. Okay? It's just a nice, there are certainly other ways you can go to solve these, but this is a nice way to do it every time to figure things out. And the goal then is, if you look at the third row here, this h is the new c3, because we most likely will have manipulated it, and it's going to be a different value at this point. And it represents c3 times z equals some constant. Well, if this is 0 and this is 0, what you really have here is hz is equal to some constant I, and therefore you can solve for z like they show you right here. And if you can solve for z, well then from this equation you're going to have ey plus fz is equal to some constant g. But if I know what z is equal to, I can solve for y, and so on, and all the way back to x. So that's what we're going to do, and they have some nice information here that you can read on your own. I'm not going to go over it. And let's get to it. So I need to solve this system and then interpret the result geometrically. That's the other thing. Depending on our results, we can see if there is a unique solution, an infinite number of solutions, or no solutions. So first thing we need to do is set up this matrix. So that would be 1, 3, -1, 15. Okay, where did I get these? The coefficients of equation 1, and then the constant. And then 2, 1, 1, 7, and then 1, -1, -2, 0. Okay, so I'm going to get my next matrix ready. And I'm going to put down here what it is I'm doing. Remember, the goal, I need a 0 here, I need a 0 here, and I need a 0 here. That's the goal. I'm going to get rid of those and just maybe put check marks there. That's a pathetic check mark here, here, and here. So the first thing I'm going to work on is right here. I'm going to get a 0 here. And what I'm going to choose to do is take 2 times, let's call this row 1 and this row 2 and this row 3. I'm going to take row 2 minus 2 times row 1 to get my new row 2. Okay, so row 2 is going to be row 2 minus 2 times row 1. Okay, so how does that work? 2 minus 2 times 1, or 2 minus 2 is 0. Bam! 1 minus 2 times 3 is negative 5. 1 minus 2 times negative 3 is 2 times negative 3. Sorry, 1 minus 2 times negative 1, that's going to be a positive 3. And then 7 minus 2 times 15 is negative 23. Okay, so I got a 0 here. Can I get a 0 here or here? Well, this is going to be easy. For row 3, I'm just going to say that's going to be equal to row 3 minus row 1. And maybe you see a different way, that's fine, but as long as you can get a 0 here, here, and here, you're in good shape. So I'm just going to take this minus this to get my new row 3. 1 minus 1 is 0. Negative 1 minus 3 is negative 4. And negative 2 minus a negative 1 is a negative 1. And then 0 minus 15 is a negative 15. And I'm going to leave row 1 alone. There you go. 1, negative 3, negative 1, 15. Now there's other ways to solve these, but this is just a nice organized method. So now I'm going to go up here, and all I need now is for this to be a 0. That doesn't look like it's going to be too pretty, but we are excellent arithmeticians, algebraicians, and we shall get this done. Okay, so what I'm going to propose is to get row 3, I am going to take 5 times row 3 minus 4 times row 2. Why? Well, a negative 20 and a positive 20 will end up giving me 0. Okay, so in the spirit or in the interest of saving some time here, I'm just going to give you the results, and you'll have to trust me. 0, 0, 0, negative 17, and 17. There we go. And then I'm going to keep these same two rows. So 0, negative 5, 3, negative 23, and then 1, 3, negative 1, and 15. So now we're in business, right? Remember, this is my X column, Y column, Z column. So from this last row, I have negative 17Z equals 17, and Z equals negative 1. Awesome. And then up here, I have negative 5x, nope, that's negative 5y, sorry, plus 3z is equal to negative 23. And without going through all the arithmetic and substitution, I'm just going to tell you, replacing z with negative 1, I get y equal to 4. And then using row 1 with these values, I would have 1x plus 3y minus z equals 15, yes. And if I replace y and z with what I know, I end up with x equal to 2. Okay? And so since we got actual numbers with no variables, and you'll see what I mean by that in a little bit, 2, 4, negative 1, we can say that this represents 3 planes that meet at the single point 2, 4, negative 1, and I think that's the first one that I graphed. 1, 3, yeah, it is. So this is actually that system of equations solved. So that point, let's see, right there is actually the point 2, 4, negative 1. Okay, that is it for now. We'll finish this up in the next video. Let's see how Blue Oyster Cult is doing. They are burning for us. We are not fearing the Reaper. I am...